Bismillah ar-Rahman ar-Rahim. As always, Assalamu alaikum, dear students, welcome. I am Professor Bashir Ammar from National High School of Mathematics. Once again, welcome. This exercise will discuss extremum of this set. So here we consider set A, which is equal to the square root of n minus the square root, the integer part of the square root of n, and in natural number, starting from 1. 1 has by the definition of the integer part, the integer part of the square root of n is less than or equal the square root of n and is strictly greater than the square root of n minus 1. If we times by minus 1, we get minus the square root of n integer part, this one, which is greater than or minus the square root of n, and it is strictly less than minus the square root of n plus 1. By adding to both double inequalities, we get the square root of n minus the square root of n. This is less than or equal the square root of n minus integer part of the square root of n, less than minus the square root of n plus 1 plus the square root of n. So we cancel these terms. From what we get 0 less than or equal the square root of n minus integer part of the square root of n, which is strictly less than 1. Then we can say that A is bounded. Thus, A is bounded. After under the grammar. 0 is the infimum. 0 is the infimum of A because 0 is equal to the minimum of A. Why? Because, for example, for n equal 1, we have the square root of 1 equal 1, and the integer part of the square root of 1 is equal to 1. 1 minus 1 equals 0. For n equal 4, we have the same thing. For n equal 3, we have the same thing. So here we find, at least we find values for n such that we have equality, and this is exactly the definition of the minimum of a set, if we can find a value which verifies this. So for infimum, we don't need to use characterization since it is equal to the minimum. How about the supremum, the sup? The sup of A will be equal to 1. 1 is an upper bound. Is it the least upper bound of this set? We will solve this later. Okay. Using characterization, of Supremum, of Sup, we will show that sub A equal 1. This is equivalent to the following. For all epsilon greater than 0, can we find x from A such that what? X epsilon from A such that what? Such that x epsilon is less than or equal 1, which is strictly greater than 1 minus epsilon. This is the second condition, and the first condition, for all x in A, we saw that x is less than or equal to 1, strictly less than 1. So we can take less than or equal to 1. The previous work shows that this is true. Remember to show that this one is also true. We have k squared, natural number. This is less than or equal to k plus 1 squared minus 1. And this is less than k plus 1 squared. This means this is equivalent to write k squared less than k squared plus 2k plus 1 minus 1, so this one, which is less than k plus 1 squared. If we take the square root, from this side we get k, and from this side we get what? We get the square root of k squared plus 2k. From this side we get k plus 1. Then we can deduce that the integer part of the square root of k squared plus 2k is equal to k. This is the trick of this exercise. Then if we take n of this form, so if we take n of this form equal natural number k squared plus 2k, we obtain the square root of k squared plus 2k minus the integer part of k squared plus 2k is equal to k minus k. This is equal to, we times by and divide by the conjugate of this number. We get from here k squared plus 2k minus k times the square root of k squared plus 2k plus k over the square root of k squared plus 2k plus k, which is equal to, here simple calculations, we get k squared minus k squared, 2k, yeah, so we get 2k over k times the square root of 1 plus 2 divided by k plus 1, and we can simplify this one. For this special choose of the form of n, we get what? Can we find a natural number such that this particular natural number verifies the property of Supremum? In this case, what we have, for all epsilon greater than 0, can we find x epsilon such that what? Such that one minus epsilon less than x epsilon, which is less than or equal 1. This is, since we take the same form and we proved previously that we have all this for any given x epsilon, just if x epsilon belongs to I, so this is true. And here we take x epsilon, we will take it from this form, 2k squared plus 2k, k squared plus 2k minus the integer part of k squared plus 2k. We take x epsilon from this type. If we can we find k such that x epsilon which takes this form, verify this one. This is the question. For sure here for and taking this form, special form. We need just one element. Don't forget this. But this formula yields to this one, which means 2 over the square root of 1 plus 2 over k plus 1 greater than what? Greater than 1 minus epsilon. Can we find k such that this is true for any epsilon? If epsilon is greater than, if epsilon is greater or equal 1, this is true. Why? Because we will get a real number which is positive real number which is naturally greater than 0 or negative numbers. Now we, for epsilon less than 1 and strictly greater than 0, we are in this case, can we solve this inequality? Actually the answer is yes. We can find k 0 such that this is true. Here we can use the fact that the field R is Archimedean, and we can calculate it explicitly. Let us calculate it explicitly, or we can just say that R is Archimedean and then k, a special k, exists for any epsilon. Since this is positive, we can inverse. We get what? We get 2 over 1 minus epsilon greater than the square root of 1 plus 2 over k plus 1. Then we get from here, we get 2 over 1 minus epsilon minus 1 greater than the square root of 1 plus 2 over k. And for epsilon between 0 and 1, this is sure. Why? Because 2 divided by 1 minus epsilon is greater than 2, strictly greater. So this is positive. Here we can take square. If we take square, so we get 2 over 1 minus epsilon minus 1 square, which is greater than 1 plus 2 over k. From what here we can deduce that 2 over 1 minus epsilon minus 1 square minus 1 is greater than 2 divided by k. From what? We take the inverse from this last inequality. we get k over 2 greater than, we take the inverse greater than k over 2 greater than 1 over 2 over 1 minus epsilon minus 1 square minus 1, which is strictly greater than 1, this one, for the same reason that we told about. Then we get this one. So it is sufficient to take k0, okay, as the integer part of all this 1 plus 1. For this k, we have the inequality, and the n, for this k, the n which takes the form k squared plus 2k, verify the property existence of the elements of A such that this is true. I hope that this helped. Thank you very much. See you next time.